consider an atom with two levels, and the cavity photon is at the same frequency. Okay? Then if these two atom and photons are not coupled, then of course the energy state of this combined system will be just like this. But then if, no, yeah, I'll go more. So if they don't interact, you can see the system has these energy levels. But if they coupled, then the degeneracy is split into something like that. So these are the mixed states. Okay? Now, if you do measurements, you will find that you have the splitting, which is coming from the field coupled with the atom. The field is coming from single photon, and the atom is 0 or 1 atom. Okay? And so you can see, indeed, you can see the splitting. And this is the AC Stokes splitting of a single atom by a single photon. Okay. So this is the atom is here. This is the microcavity with single photon. You can see it.
Is it done at room temperature?
Yeah.
Or low temperature?
I believe it's room temperature. Yeah. Another fairly straightforward case is the Modoc laser that was developed in the late 1960s, so many years ago. Okay? And we know that you have these periodic pulses. And if you do the Fourier transform of the periodic pulses, what you see is you have the frequency cone. Okay? And the frequency cone has this line width determined by the inverse of the total length of the series of pulses. Okay? And then this width of this frequency cone is given by this single pulse width, inverse of the single pulse width. Okay? But the interesting thing is, if you could make these pulses going forever with exactly the same shape, then of course the line width will be 0, infinitesimally small. Okay? And that means you have these femtosecond, suppose these are femtosecond pulses, so each pulse is femtosecond. But if you look at the frequency cone line width, it's very, very narrow. So this source could be used to do precision spectroscopy with very, very accurate frequency resolution. And you have the time resolution of femtosecond. Okay. Well, so this is very nice, and that got Hensch and Jane Hall the Nobel Prize. But then this advancement actually branched out. One is you can pick out one single pulse. And in that single pulse, you see there are carriers here. And they can control the carrier and this envelope very precisely so that this pulse is different from that pulse because the field variation is different. And therefore, if you do measurement, especially nonlinear optical measurement, using this pulse or that pulse, they will give you different results. Although from freshman or undergraduate physics, you will say these two pulses are the same. But anyway, if you non-pick out one well-defined pulse like this and amplify it, you can amplify it to very high energy per pulse, such as 0.1 joule, and the pulse width is 5 femtosecond. Now you can see the peak power can be very high, and if you focus it down, it can get to 10 to the 24 watts per square meter. And that's very, very high, breaks down everything. It can start nuclear reaction. Okay? But this can all be done on a tabletop. So it's a tabletop terahertz or T-cube laser. Okay? Now, with such a high field intensity pulse, then you can see that at 10 to the 19 watts per square centimeter, this so-called pondermotive potential is already 1 megavolt. And that's larger than the rest mass of the electron. So therefore, you cannot use non-relativistic calculation on interacting with electrons. Because if you use non-relativistic calculation, then in half cycle, the velocity of the particle is already larger than the light velocity. Okay? So in this case, you can talk about relativistic electron dynamics with laser doing something to it. And what it does something to it, the best thing is the laser particle accelerator. In other words, you can use such short pulses to accelerate an electron, for example. And that electron energy can be gained to a very high level. And I understand last year, the Institute of Optics in Shanghai got the record of electron energy got to 1.8 GeV. Okay? So 1.8 GeV is already close to the energy of synchrotron radiation people use. So what they are planning to do is to put an undulator in the path of the electrons, of the accelerated electrons, and to see the UV, at 1.0 GeV, you only see the visible, but you can see the synchrotron radiation coming out. Okay? So if this gets advanced and becomes more successful, then you can use essentially tabletop lasers to replace the synchrotron radiation. And that would be certainly very exciting because everything could be more easily controlled. And then the other branch I want to talk about is a very strong nonlinear optical effect. There are many, quite a few very strong nonlinear optical effects, such as infrared multi-photon excitation to dissociate the molecule. That usually takes something like 30, 50, even 100 photons. That gets to excite the molecule and then dissociate it. Well, of course, this is a very, very high nonlinearity, considering that you involve in one step 50 photons. Okay. Well, let me focus on this high harmonic generation and using it to generate the attosecond soft X-ray pulses. And this, again, it's a very high nonlinear effect because we're talking about generating harmonics more than 100 harmonics. Okay? And so, of course, it cannot be a perturbation process. It has to be a so-called non-perturbative effect. Well, usually in physics, whenever you get to the strong coupling limit, theorists will give up because it's so hard. But here, the nice thing about a laser is even though it's so strongly nonlinear, you can still understand it very easily. And this particular process was explained by Paul Corkum. And what he showed is if you have a laser cycle like this, high field, then at some point, say 1, the field is intense enough so it can distort the potential around a nuclear this way, because the field is going that way, and you can that way, and you can see the potential around a nucleus will be distorted like this. Now, the electron in the ground state, if this potential is distorted big enough, then the ground state electron can tunnel through the barrier and become ionized. Okay? So the electron leaves the nucleus, but the field is still on, it's still positive. So the field is going to accelerate the electron that way, in that direction. And then the field become negative. When it becomes negative, it will slow down, and eventually it will turn around and come back. And when it comes back, at some point, it becomes accelerated by the negative field. And then when it comes back, hit the nucleus, then we have the so-called Bremsstrahlung radiation. And this Bremsstrahlung radiation happens in such a short time, and so therefore it gives out an attosecond pulse. Okay? And of course, the energy released is the energy gain in the electric field, and it's in the soft X-ray. Okay? So that seems to be very easy to understand. And now this attosecond pulse can be generated at will, in the sense that you can control the electric field very well, so that you know when the electron is coming out and when it is returning to the nucleus. The trace can be predicted, so you can also think about the electron coming back, and instead of an atom, it's a molecule. Then when the electron coming back to hit the molecule, or the ionized molecule, the electron will be diffracted. So you can get single electron diffraction from the molecules. And if you adjust or control the time, you can see the dynamic variation of the molecular conformation. So this is all very exciting. But then we talk about the so-called high-order harmonic generation. And again, it can be easily understood because now you see, suppose you have a laser with many cycles like this. Then on each cycle, you can have an attosecond pulse created, like what I said. Okay? So every cycle, you have an attosecond pulse. And you have many, many attosecond pulses, and they are periodic. And if you can get it over a very long time, series of pulses, you will get a frequency cone with very narrow line width. Well, that's the same as the frequency cone we just talked about, but the difference is this will be in the soft X-ray. I mean, all the way. It can be extended to the soft X-ray. Okay. So this really shows that the frequency cone is now possible to be extended to the soft X-ray. And actually what was more recently done was by John Ye's group at Colorado. And they showed that using a cavity, and you put gas in the cavity, and then use the high-intensity laser, you can generate frequency comb all the way to the soft X-ray or VUV range or XUV range. Okay. Well, what is great about this? Well, we just said that if we have this very narrow line width, in the visibility stage, you can get to 1 Hertz line width, or even less. So the resolution, spectral resolution, is 10 to the 15. Okay. Now, if you can get to the XUV, the frequency of XUV is 10 to the 16. If your line width is still 1 Hertz, your resolution is improved to 10 to the 16. Okay? And with 10 to the 15 resolution, people have already done all kinds of interesting, great fundamental physics to the precision spectroscopy to determine the fundamental constant, all these things, and even talking about to check whether the fundamental constant is changing with time. Now with 1 order of magnitude improvement in precision spectroscopy, you can see the world is certainly going to change, or in the research world. Okay. So that's what I would consider also very exciting. Well, this is just an example showing the harmonic generation. And then, of course, we have the new field coming out from this big laser, high energy, high intensity, that will allow you to create plasmas. And the final goal is the fusion. But before you reach fusion, you have a new field in physics called matter at high energy density. Okay? But that is coming from the implosion, so make the density very high. But anyway, this is just an example of the high density matter field. So the current topics in nonlinear optics, hot topics, is attosecond electron dynamics, high field physics we talk about, frequency comb with precision spectroscopy, and we can talk about nonlinear optics with the frequencies comb, and nonlinear optics of cold atoms and molecules. That's relatively easy to do. And the X-ray nonlinear optics, anticipating these X-ray lasers being available, and then the high energy density matter. So my last question is, these are all big setups, huge amount of money, and if we don't have money, we don't have a big space, what can we do? So for the small fish, what can we do? Okay. So obviously, we all belong to this group, and I would say we just have to struggle in the sense that we have to develop new technology, and we would talk about characterization of new materials, such as graphene, topological insulators, and so on. And so far, nonlinear optics has been done more or less more with intensity signals. But for optical waves, intensity and phase are 2 parts. And if we don't know the phase, we lose half of the information. So that probably should be considered more. Nonlinear optics with frequency comb, in particular, frequency combs applied to condensed matter. So far, frequency comb is such a great tool, but for some reason, no one can think of good problems to use it on condensed matter physics. And exotic nonlinear optical effects and then laser manipulation of the materials, and in the sense of coherent control and induced phase transition, induced metastable materials, and so on. So this is, I think I sort of killed all the time, and I was going to talk about, as a small fish, what we did, but I think probably I should stop here. Okay. Thank you very much, and I do have a last slide. That must be correct. That must be correct. Thank you.
Perguntas? Fontana?
Are there any commercially available terahertz sources based on nonlinear optics devices?
Terahertz source commercial one?
Commercially available at the present moment?
I don't know. I mean, because it's very easy to set up if you have the femtosecond lasers.
I know,
But
but everybody does it in the lab. I want to know if people are selling that commercially.
No, I don't think it's available yet. You're talking about a little box,
Yeah,
with fiber lasers and so on. Yeah, I think people are working on it, but I haven't heard commercial products.
More question?
I'd like you to comment about what I would like you to comment on your impression on the application of nonlinear optics for quantum computation.
Quantum computation.
Yes. What are you feeling on this field?
I have no feeling at all because I don't know whether quantum computation will ever take off because you look at all the computer companies, which computer companies are really seriously working on it? I think, you already considered the next stage of quantum computation.
We need 40 years more.
If in 40 years you have quantum computation, it's wonderful.
Another question? Yeah.
On a completely different note, regarding your first part of your talk, if you do have an excess of students, bring them on. I mean, we want them. That Brazil has a program for Science Without Borders to both bring researchers as well as students to come study in Brazil, as well we can send students abroad. So do you think, I know, most of us have spent some time in the US. We see all the Chinese students going to the US mostly, and they have good reason to do so. But we now are in a position that we can pay students to come. Do you think this bridge could be built?
I think you should spend some effort to do that, because there are many Chinese students. You will not be able to compete with US and Europe to get the top batch. But don't go to the big cities to get students. But if you go to the smaller cities, they could have students who are interested in coming out. And in fact, almost all countries are trying to get foreign students. The more developed countries. Europe is working hard to attract Chinese students and students from other Asian countries. They all complain that US got all the good students. Okay? But on the other hand, Taiwan is trying to get international students. They set up a special program to attract students to the academic synagogue. And what they got are the Southeast Asia students, Indian students, and mostly those students, occasionally some East European students. So again, East European students could be very good. So you have to reach out to give them the information that you want them. In Taiwan, they send out pamphlets. So they really advertise. And I'm sure that the Chinese universities are trying very hard too. Because every bigger university all has an international center. And that means they have enough foreign students already.
Hughes has one question, right?
Yeah.
Back to science, could you comment on how it stands on nonlinear optics for surface and chemistry? This subject we know that Berkeley was leading a long time ago.
Excuse me.
Yeah.
Maybe I can add another question. Would you talk about this field of laser-induced phase transition? Because for me, it seems to be a very interesting subject, and it does not require very much equipment, too much money to go in that.
Yeah.
It will just require good materials, probably.
Right.
Yeah.
Right.
So
But this
can
is
you
a
comment?
material problem.
Yeah.
I mean, you have to find good materials like VO2.
Like that.
But not that many. Actually, another interesting area is laser-induced chirality. You transformed the right chirality to left chirality. That may be easier to find the materials.
You mean organic materials?
Organic molecule, switching the chirality, and the function completely changes. It has bigger effect than the solid-state phase transitions.
Okay, so VO2 is a
It's
nice
possible.
example, but
Yeah.
do you remember of other possible materials that could be exploited?
I can't. I mean, I know that, of course, you can induce phase transition in superconductors, right? And people use it as a detector to detect infrared photons. As long as you absorb one photon, it heats up the junction and goes to the normal junction. That's being used. The others, you have magnetism and so on, but those are not being used.
Yeah, and also this field of magneto-optical nonlinear effects. Nonlinear magneto-optical effects may be
Right.
one area very interesting.
Yeah, if you can find some usefulness.
Mais
Oh,
perguntas?
sorry.
Hughes has another
So,
question.
Theo, what would you like to know?
The original question, he wants to know about this original question.
Yeah. So what's the question now? You want to know the surface? Yeah. Yeah.
But you have another question.
It's the question. It's the original one. It's the same.
Okay. So, yeah.
Ask you to comment on how it stands in terms of all the development nonlinear optics applied
To surfaces.
surface physics, chemistry, water,
Yeah.
and so many things
Yeah.
had leading
Yeah.
Berkeley.
Yeah. Well, I mean, we're still working on it. It's maybe you want me to give 5-minute talk?
I would say
Yes. Wait a minute. I don't know how to. Oh. Okay. Let me try to be fast. Okay. This is some frequency generation, and by symmetry, we know that the bulk and surface usually have different structural symmetry, and therefore they have different nonlinear susceptibility tensors. And you can choose the polarization combinations of input and output to selectively suppress the bulk contribution. In other words, make the electric dipole contribution 0 for the bulk. But the surface always has the electric dipole contribution. So by using polarization scheme, you can suppress the bulk contribution and emphasize the surface. And so with this, we could, so forget about the details. We can see that, for example, using an infrared tunable light, I can excite the vibrational resonance and get some frequency out. And when you hit the resonance, you know the output will be enhanced. Therefore, you get a resonance spectrum. This way, you know where the vibrational resonance is. But if I have the bulk already suppressed, bulk signal suppressed, then the signal is coming from the surface, and I gain the surface information or surface structural information. Okay? So that's basically the idea. And the setup is basically one tunable laser and another visible laser that can be fixed. And so you do spectroscopy by tuning the infrared. So advantages, you have sub-monolayer sensitivity, surface specific, and it's a coherent spectroscopy technique, so it's highly directional, and you can do remote sensing. You can have a temporal resolution. If I use femtosecond pulses, I can have femtosecond resolution, and applicable to all interfaces. Okay? So most importantly, it's the barrier interfaces that no other technique can be used to probe. So there are many applications, but I just want to show you the surface specificity part. You can see that if I have a system like this, silica and this hexadecane long chain, so if you do infrared measurements, what you will see is huge CH vibration, right, because of the HD here. But in this case, we see essentially nothing in the CH stretch region. Okay? But if you put one monolayer of OTS, it's a silane like this, suddenly you see the CH stretch. So obviously the spectrum is coming from the monolayer of OTS. If we replace this HD by CCl4, we get essentially the same spectrum. So that clearly indicates the spectrum is coming from one monolayer. So that shows the surface specificity. And so what kind of applications? We can do barrier interfaces.